Okay. So Dr. Stephen Hickman has been a research geophysicist with the USGS Earthquake Science Center in Menlo Park since 1989. He's currently director of the Earthquake Science Center. His research focuses on deep borehole studies of the interaction between stress fractures and fluid flow in deep geothermal systems and the physical and chemical processes controlling faulting and earthquake generation along active faults. He received his bachelor's degree in geology from Earlham College and a PhD in solid earth geophysics from MIT. He received the Superior Service and Meritorious Service Awards from the U.S. Department of the Interior and the 2014 Paul G. Silver Award for Outstanding Scientific Service from the American Geophysical Union. Stephen Hickman.
So thank you for that introduction, and thank you all for coming here. I first wanted to welcome you all to the U.S. Geological Survey. This is our home, and you are in Building 3, and this houses about half of the people who work in Menlo Park on earthquakes. The other half are in the building next door. And the Earthquake Science Center has about 145 scientists, most of them in Menlo Park, some in Pasadena, some in Seattle, who work on basic research, trying to understand what makes earthquakes work, what controls the severity of shaking, what controls their timing. We also carry on extensive monitoring efforts and produce a lot of different very practical hazard assessments. So we like to think that we put science to action, trying to understand earthquakes better, and in the process make this a safer world. Now, I'm going to be talking a little bit, this is sort of Earthquakes 101. So I was asked to talk a little bit about earthquakes, and I'm going to assume that I know how to work this. Oh, wait. Go do. Am I doing something incorrect here? Oh, there we go. Okay, that's better. Okay, so we all know about plate tectonics. Plate tectonics, basically we have the plates drifting around on the surface of the Earth a few centimeters a year. That is essentially the driving force for most of the earthquakes that we see. They move steadily. If they move steadily at their boundaries, we would not have earthquakes, but they don't. They hang up at their boundaries and then they break. And this is a close-up here of the California. We are right now right about there on the peninsula. And this is the plate boundary between the Pacific and North America. The Pacific moves at about 48 millimeters per year relative to North America, and most of that motion is accommodated on the San Andreas and associated faults. For most of its length, the San Andreas locks up and only is released during earthquakes, but in Central California it moves quietly, shown here in blue, and actually creeps quietly along. The San Francisco, now called the Great San Francisco Earthquake 7.8 in 1906, 110 years ago, occurred on this segment, all the way up there. Loma Prieta, Parkfield earthquake recurred down there when I was actually standing on a drilling rig, and 1857, 7.9 was on the southern San Andreas. So what is an earthquake? This is a cartoon which I borrowed from Doug here. It's basically to illustrate what happens during an earthquake. So you imagine here's a fault, and this is one plate, tectonic plate, and here's the other, and they're stuck. And there's a fence right across it. As the plates try to drift and the friction holds the fault together, the fence bends and the earth acts like a giant spring. It stores up the energy that will then be released when the earthquake happens. The rock suddenly slips, releases the elastic energy that's stored in the surrounding rocks, and that gets radiated away from the fault, and that's what you feel as an earthquake. Then you start all over again and you start the cycle rebuilding the strain along the fault. This is a strike-slip fault. Things are moving side by side, just like in the San Andreas. What kind of waves do we have coming out of an earthquake? P waves are compressional waves. I'm speaking to you right now with compressional waves. Those are sound waves. Compression and rarefaction along the direction of propagation. Shear waves only transfer through solid medium, and those are side-to-side motion along the direction of propagation. In an earthquake, the P wave travels a lot faster, about 70% or so faster than the S wave, so it's the first wave to hit you, but it's typically smaller in magnitude. Most of the damage is done by the S waves. That has the most severe shaking. And then following the S waves are what we call surface waves, which travel along the surface of the earth like ripples in a pond. And these long period waves can actually go to considerable distance and affect tall buildings at hundreds of kilometers from an earthquake. Here's my earthquake basics. So if you remember anything about this talk, remember some of these facts, which are kind of interesting. I mentioned before 80% of earthquakes occur on tectonic plate boundaries. If you increase the magnitude of an earthquake by a factor of 1, you've increased the energy released by a factor of about a factor of 30. So the difference between a magnitude 5 and a magnitude 6 is the magnitude 6 releases about 30 times as much energy. So it's a big difference. Also, there are a lot more small earthquakes than there are big earthquakes. If you look down here, the Earth produces about 1 magnitude 8 every year, 15 magnitude 7s, 13 magnitude 6s, 1,300 magnitude 5s, 13,000 magnitude 4s, and 130,000 magnitude 3s. Those are basically occurring constantly. So there's a lot more small earthquakes than big ones, and one of the huge scientific questions is, why do most earthquakes stay small? What makes some of them grow into giant earthquakes that cause damage? Also, most earthquake damage comes from ground motion, that's the shaking, but there are also other effects I'll be talking about later. And the intensity of the shaking usually drops off as you get farther away, but can be affected by local structure, focusing of seismic waves into your site, or if your site is soft, it can amplify the shaking. So 2 questions we like to ask are, what is the likelihood of an earthquake, and what is the shaking going to be from that earthquake? Let's look at the first question first. There are a bunch of studies been done. I'll be mentioning one, a new report. The probability of fault rupture was calculated as part of this California working group study called USERF-3. Came out in 2013 and then again in 2015. That just tells you how often a fault is going to go off in an earthquake. And then once it goes off, you want to know how hard is the ground going to shake? What are the effects of that earthquake going to be? And to answer that question, we do sometimes scenarios where we take a fault, we say it's going to go off in a particular kind of earthquake, let's see what the ground does. Or we add up all the earthquakes that might be affecting a particular source, the potential earthquakes. So you're sitting here, maybe the Hayward will go off, the San Andreas, the Calaveras. You add up all those effects, their probabilities, and then you calculate what the probability of you experiencing a certain shaking over a particular lifespan or time period is to the cumulative effect of all those earthquakes. So I'll talk a little bit first about the probabilities, the fault rupture probabilities, and how do we know? There are a lot of ingredients that go into these fault rupture probabilities. One is seismic monitoring. You've got to keep track of the earthquakes. They're telling us where the faults are, and they tell us, especially if they're bigger, what the timing and periodicity is of potentially dangerous faults. The USGS, along with multiple partners, UC Berkeley, Caltech, California Geological Survey, maintains a very extensive seismic network throughout California. Here are all the partners. I won't bother reading the acronyms. But there are a lot of seismic stations in California and many more going in for earthquake early warning, which Doug will be talking about. And this is the diagram of what they look like, in this case solar powered. There are also seismic stations up in the Pacific Northwest, part of the Pacific Northwest Seismic Network. We have an office up there in Seattle, work with the University of Washington, University of Oregon to maintain those stations, and both of these are being used in the Shake Alert Earthquake Early Warning System. This is a map showing what kind of seismicity we have seen in the San Francisco Bay Area over the past 30 years, just looking at magnitudes greater than 2. The thing that I always like to tell my kids and anyone else who likes living in this area is we live in a beautiful area because we are at a plate boundary. The Santa Cruz Mountains are being pushed up, the bay got pulled apart. The topography is steep and interesting because the Earth is moving here. The downside of that is we're not in Kansas, we have earthquakes. So the same thing that makes the topography, that makes the bay, makes the coastline, also makes the earthquakes. These gray lines here are the faults. San Andreas is the famous one. I'll be talking about the other ones too, but you'll notice that some of the faults are really lit up by these small earthquakes. You can tell where they are. Other parts, they're basically completely quiet. They're completely locked up, not producing any seismicity. They're waiting for something big to happen. Other parts, we get a lot of earthquakes. The Hayward fault in particular does a combination of creeping and producing small earthquakes, but other parts are just locked up. Another thing, in addition to seismic networks, we have GPS stations all over the western U.S. Some of this was installed as part of the Plate Boundary Observatory. These are very fancy GPS receivers anchored in very stable ways to the bedrock, but not too dissimilar from what you might have on your cell phones. They're just a lot more high-tech and more stable. These arrows show the velocity of the Earth recorded with these GPS transducers. You can see that the Earth is a very unstable place and things are spinning around. These GPS stations allow us to determine how fast strain is accumulating along faults, how rapidly is the stress and strain building up along a fault. That's an important ingredient in determining the probability of a new earthquake occurring. How fast is the energy building up? And also, once a fault goes off, we can learn about how the Earth crust relaxes. It's not quite as simple as I showed before. The earthquake slips in an earthquake, but down you go deeper, the Earth is more ductile. There's a sort of a viscous relaxation that occurs, and we saw with Napa, even after an earthquake, the shallow fault can keep slipping. So it's not quite an on-off thing. We're trying to understand as scientists what's happening with all these transients, because these transients load the fault for the next earthquake, either from the side or even from below. A lot of the stresses that drive faults come from below. Another ingredient in the fault probabilities is we dig trenches across faults. This is an example from a fault that Jim Leenkamper and his colleagues with USGS dug in the Hayward Fault across the bay. They look at disrupted soil horizons. They date carbon samples that are trapped in falls on the downside of little faults like this one. And through a lot of really careful work, we're able to construct chronologies like this. And this is a chronology showing the history of past earthquakes on the southern Hayward Fault over the last 2,000 years. So this is pretty amazing. You get a 2,000-year history of a fault by digging a number of trenches like this. And what you'll see is that they're relatively regular. Each one of these things is an earthquake. Captured 12 earthquakes in 2,000 years. The last one was 1868, magnitude 6.8. And the mean recurrence interval is 161 years, plus or minus 65. And it's the plus or minus that matters because that affects the probabilities. So it's about time. We could be overdue, we could be underdue, depending on where you put the plus or minus signs. But this is a very regular system, and the Hayward Fault is definitely a regular player in producing large earthquakes. So these things all led into what's called the Uniform California Earthquake Rupture Forecast, and it was released officially about this time last year, combining geology, geodesy, I mentioned the GPS receivers, seismology, where are the earthquakes happening now, where are the active faults, and then the paleoseismology, like that trench I just showed you. There are a lot of people working on these different aspects. USGS, Southern California Earthquake Center, California Geological Survey, California Earthquake Authority, all working together on this model. This model is a great improvement from what was done before because you see many faults. Each of these red lines is a fault. The redder they are, the greater the likelihood that that piece of a fault is going to participate in an earthquake in the next 30 years. And you can see there are a lot of them. They're all allowed to interact in this model. They all remember when they last went off. So if you know a particular segment went off 150 years ago, you're kind of late. If it went off 50 years ago, it's not so bad. And you add all those things together with the geodetic strain accumulation, the paleoseismicity, you run theoretical models that allow one fault segment to jump over to another. So we know that faults can jump between segments now, and that's included in this model. And then all the uncertainties are captured in this completely illegible table, which I just put up there to show you that if you wanted to go to the website and you look under USURF3, Google it, whatever, you'll find a table of probabilities for earthquakes of different sizes in different parts of California based upon this latest and greatest model. Now I'm just going to zoom in on the San Francisco Bay Area because that's where we are. So here we are. Here's the San Andreas Fault. And this map just shows the probability of an earthquake of greater than magnitude 6.7 in the next 30 years occurring on one of these segments. So the Hayward has about a 32% probability, San Andreas about 22, so the Hayward's a little later in the cycle, more likely to go off, but not negligible probability for the San Andreas. San Gregorio, which goes offshore, is about 9, and we have Green Valley and others which are lower, and then the Rogers Creek continuing into the Hayward, as David mentioned, could actually rupture all at once if it decided to and go across San Pablo Bay and make a rather large earthquake. If you look at the sum total over this map of what the probabilities are, magnitude 6 over the next 30 years, 98% chance, virtual certainty. Of course, the Napa earthquake was a magnitude 6. 6.7, which is kind of a threshold for us, that was the Northridge earthquake. Loma Prieta was 6.9. You're getting into serious earthquakes. Napa was serious, but 6.7, 6.9s can cause a lot of damage. And there was the 7 in Japan, which just occurred, but you know that was pretty serious. The 7 that occurred in Japan is a strike-slip fault, pretty much analogous to the Hayward, and it's something that we could be seeing here stateside in the next 30 years at these probabilities. Then as you get to bigger and bigger earthquakes, the probabilities drop down. The San Andreas Fault movie was wrong. We don't get magnitude 9.3 or whatever they say on the San Andreas, but we could get above 7.5. One of the interesting things about the San Andreas Fault is it remembers what happened. This is just a timeline. Each of these little blue circles is an earthquake. There's the 7.8 in 1906, and you can see before 1906 there were a lot of earthquakes, but after 1906 the stress was relieved along the San Andreas Fault, and we think it kind of turned off the stresses on the faults around it, produced sort of a stress shadow that caused the seismicity rate to drop off for a while. It's starting to pick up. There's the Loma Prieta and 6.9, and so we're getting a little bit more seismicity, but for a while the Bay Area was very quiet. That was the first part. So we know a lot more now than we used to about how often the earthquakes occur. When they happen, then what can you expect? One thing to you really need to realize is that big earthquakes produce a lot more shaking than small ones. That's pretty obvious, but only the difference between a magnitude 6, like South Napa, and a 6.9, like Loma Prieta, can make a huge difference in the amount of shaking that the area is actually going to see. This map here is something that was run as a scenario for a particular earthquake. Of course, the Napa was observed, this was observed, and then they were smoothed. These red lines here, damage to engineered structures, modern structures and buildings would be expected in the red zones. Older houses, chimneys, and masonry in the more pinkish sort of zones, yellow, things thrown from shelves, and then you start waking people up. It's much more benign. So things start to get a little dicey when you get into the reds, much smaller there. And of course, there were some regions quite distant from Loma Prieta that were badly affected, as I'll mention here in a minute. So trying to predict ground motions is a huge deal for people working in the earthquake world. It's a very complicated topic, so I'm not going to talk about it, but just in a nutshell, any given earthquake of a given magnitude, the ground motion you're going to experience depends on how far away you are from the fault, what the rupture geometry is, and particular directivity. If the rupture starts at the southern end of a fault and grows towards you, you're going to feel a lot more shaking than if it grows away from you, just like a train coming at you. Also, if a lot of asperities break quickly in a fault, it makes higher frequency. If it ruptures more smoothly, it makes low frequency. It's a fascinating topic. People have studied this a lot, and those frequencies generated by these faults when they rupture have a big impact on engineered structures because they have their own sensitivities to different frequencies. Geologic structures near a fault can focus the seismic rays like lenses focus light. So an earthquake produces rays. If it's focused into a basin, the basin can keep that energy and reverberate like a bowl of jello. Can also focus it to a sharper concentration, bounce off the boho. There are lots of interesting things that can happen with earthquake rays that don't necessarily go the path of least resistance. They can bend around. And then shallow soil properties, soft soils, as I mentioned before, will tend to amplify ground motions relative to harder soils or bedrock. So this is just some examples here showing how basin structure and soft soil geologic conditions can make a difference. The Cypress Viaduct in Oakland, which is a considerable distance away from the Loma Prieta earthquake, as we all know, was seriously damaged with fatalities in that earthquake. You can see here seismograms from the event showing relatively small vibrations shaking on bedrock, but much stronger on soft mud and less so in sand and gravel. And this amplified shaking in the soft soils was a key contributor to failure of these kind of structures. Similarly, in the Marina District, lots of damage done even though it was relatively far away from the fault rupture. Another point that we emphasize a lot really is that we are lucky in that we live in a place with modern building codes where the codes are enforced. A magnitude 7 earthquake in Haiti, for example, where the building codes were poorly enforced, left more than 160,000 people dead and 1.5 million homeless. So that there's a disproportionate impact on developing countries for earthquakes. We see this all the time. And Ecuador casualties are still climbing because of buildings that fell over in an earthquake that in an ideal world would have stood up. Another way so that's a little discussion about what causes things to amplify or change shaking. I mentioned scenarios. Here's a forward-looking model for what would happen if we had a magnitude 7 earthquake on the Hayward. Similar scale to what I showed before, but now it's in modified Mercalli or MMI. But think of the MMI of 7, which is right about here, in the orange, being the threshold for damage when you start to see some modern structures suffer damage. So a pretty big area, very large area affected by this. Scenarios are being run for the Hayward scenario now on the impact of this exact earthquake on infrastructure, liquefaction, and other effects. And this was actually run through a three-dimensional model. So there's a 3D geological model. The fault was allowed to creep a little bit as we observe it to do so and relieving some of the stress. And that And we ran multiple sort of permutations of this model to test the influence of the assumptions about creep relaxation of stress and rupture directivity on ground motions. So that's one way to get at it. Now, up to now, I've just been talking about ground shaking, but there are other things that earthquakes do. They cause the earth to liquefy. This is from the Niigata, Japan earthquake in 1964, 7.4. The soil liquefied under these buildings and they literally tipped over. So liquefaction is just the shaking of a sandy soil, has a lot of pore space that collapses, the water can't get out fast enough, and the pore pressure basically pries the grains apart. It's like quicksand. And if you don't have deep pilings, which people do now in San Francisco because there are many liquefiable deposits in San Francisco, if you don't have deep pilings through to more solid soil or bedrock, this kind of thing can happen. You can also trigger landslides. There are a lot of landslides triggered locally in the Northridge earthquake. Here's a very large one triggered in El Salvador, went out right into this village. And you can get tsunamis, as we all know, from the disastrous Tohoku, Japan earthquake in 2011, a magnitude 9.0 that had run-ups as high as 40 meters above sea level and focused into various channels. This was an unusual earthquake. The seafloor flipped up where it met the trench. There were huge displacements at the seafloor, much bigger than people had seen before, and that's forced us to rethink how some kind of subduction zones behave in great earthquakes. This is a simulation of the Tohoku earthquake by NOAA, showing that the waves from that earthquake traveled all the way across the ocean, and we even saw very small tsunamis here on the coast of California. So as we know, and there's also in 1700, there was a tsunami here in Cascadia, which traveled across to Japan and actually caused some tsunami inundation there. So it goes both ways. Rapid response to USGS earthquake hazard products. I think if you live in this area, you must have gone into the recent earthquakes page. Every time there's an earthquake, people log on and see what's happening. You can find out about that earthquake. Here's the Ecuadorian earthquake. We also have other products which you should take a look at. Did you feel it? Is if people feel the earthquake, they report in and you get a very quick picture of where the felt area was. This was the Mineral Virginia earthquake, but we get these all the time, of course, in Southern and Northern California. That's people reporting in. Shake Map actually takes measurements from our instruments in the ground of ground acceleration, ground velocity, and smooths them to produce basically quick pictures of the intensity of ground shaking. That's then fed into something called ShakeCast, which is provided by individual companies. Individual companies can sign up with ShakeCast to get immediate feed of Shake Map, so they know they have a facility at a particular place. How much did the ground shake? The company then beforehand puts the fragility information from their buildings into this code, and the code will tell them that they should prioritize inspection of certain aspects of their buildings and certain locations of their infrastructure based upon the Shake Map and their own fragility curves. This has been something that's been very popular with utilities and other people who have dispersed infrastructure and need to prioritize repairs. Pager, this is something that's called prompt assessment of global earthquakes for response. This is something that was started in response to requests by the State Department and other people to have quick assessments of big earthquakes internationally and what their impact might be. So this is another thing that the USGS runs. This gives an estimate of casualties, how many deaths are likely to result from an earthquake, and what the damage is likely to be around the world, and so people can start responding more quickly. National Seismic Hazard Map. This is integrating a lot of this information into a probabilistic framework. We're just trying to show as a function of color what the chance of you seeing, in this case, the chance of you exceeding certain levels of horizontal acceleration going up to 1g, that's the force of gravity, over the next 50 years. And this is contoured in 2% probabilities, which is often used in building construction and codes. So obviously California has a high probability of seeing large accelerations, as does Cascadia. Cascadia both from great subduction zone earthquakes and from crustal faults overlying the subduction zone. These maps have been very important. The most recent one was released in 2014. It was just revised for injection-induced seismicity in the central US, but it's used for building codes, insurance rates, risk assessments. It has a lot of impact. The public and media really care about earthquakes. The New Yorker article came out about Cascadia, a bit overstretched on some of the details, but it was very important in that it raised awareness of what was coming. And the San Andreas movie, of course, was a showstopper in this area. And the last thing is we do a lot of outreach and public education. Various kinds of pamphlets are produced in collaboration with these agencies, and also scenarios run to predict how much shaking is going to be from scenario earthquakes. And then these scenarios, like the shakeout, were used to simulate what was going to happen in a great Southern California earthquake, became the basis for various sort of practice exercises. So that's the end of my talk. If you want to learn anything more, just go to the USGS website, and you can find out more about preparedness, earthquakes, hazards, and anything else you're interested in. So thank you.
So I was really impressed with when I wrote an article on the Nepal quake, which was published in Make magazine, and one of the things that I did as part of that article was I looked at the pager data for that earthquake and compared it against the actual results, and I was very impressed that it was very close, and they accurately predicted that the number of deaths in that quake, and so it was a good system. Every time I think I feel an earthquake, I have a bookmark. I'm sure we all do, right? We jump right onto it. I have it on my device as well, and what was that? So I think.